Okay, so what we're going to be looking at here is we are going to be looking at the review for the second test. Now, this test basically deals with the derivatives that we've been practicing over the last little while. But I do want to say I'm not going to walk through how to do every single problem. There are quite a few problems that are very similar to each other. And so while we're looking at these problems and we're trying to find certain derivatives, I'm not going to say, okay, we have to use the power rule here every single time, or we have to use the quotient rule or the product rule. After we've seen it a couple times, I'll write all the answers down so you can check them. But some of them might not be explained. And if you have any questions about those, please let me know. So here's the first question. This says, find the limit as h approaches 0 of f of x plus h minus f of x all over h of f of x equals 1 plus sine of x at x equals pi. Now, you'll notice that we look at this and you're like, oh, crap. You see the limit as h approaches 0. You're like, oh, shoot. Luckily for us, however, even though this is bad, this is still just the formal definition of the derivative. The reason why that's nice for us is that means although this is the formula, I don't have to use it. I can still just take the derivative of this. So I can say real quick that f prime of x is equal to the derivative of 1 is 0. The derivative of sine of x, is cosine of x. So there is my derivative, and then I take pi and I plug it in and I get the cosine of pi, which if you put that into your calculator, you would find out that that is negative 1. So I look at it and I'm like, okay, that's negative 1. I can deal with that. That's fine. That's my answer. Luckily, again, for us, this is just asking us to take the derivative. But that doesn't, again, mean that we are going to necessarily have to use that formula. Okay? So here's another one. Find the slope of the tangent line of this one. So you'll notice, again, it wants it at x equals 1. Well, another name for the slope of the tangent line is the derivative. So I've got f prime of x equals, we just use our derivative formula, 48x to the 15th minus just using the power rule here, plus 3. And then I take 1 and I plug it in, 48 times 1 to the 15th minus 24 times 1 plus 3. That's 48 minus 24 plus 3. If you put that into your calculator, you get 27. So 27 is the slope of the tangent line of this particular function at x equals 1. Now, on these functions right here, what we have to do is we have to graph these on our calculator to see what's going on. When I graph, because I want to know where it's differentiable. So I graph this on the calculator. When I graph it, what it looks like more or less is I get this graph that looks kind of like this, and it bounces. It's not exactly right, but that's pretty close to what it looks like, more or less. You'll notice right there in the middle that there is a corner, so we would say that this function is differentiable everywhere, but, because that's, again, I can take the derivative anywhere, but where that corner exists at x equals 0. So that is how I tell whether or not the function is differentiable. All right, so again, we just graph it. That's the same thing holds true for this problem. Like I just take my calculator out and I graph it on this one. Although it's got a bunch of curvy things, like I'm looking at it on the calculator right now, and it kind of does this. Kind of goes down, then up, and then it kind of like levels off right there, goes up, and then down like that. And it's kind of symmetric. That's a really poor drawing. But there are, even though it goes back and forth all over the place here, there are no corners or cusps or any sort of discontinuity. So this would be differentiable everywhere. I can find the slope of the tangent line at any point, and it's not that big of a deal. It's pretty easy to find, actually. So that is differentiable everywhere. Again, hopefully that one makes sense. This next one's easier because we already have a graph. So I would say that this function is differentiable everywhere, but, and again, I'm looking for either a corner, a cusp, or any sort of discontinuity. So in this case, I would say everywhere but x equals negative 3. Is 1, and then at x equals 0 as well. At negative 3, we've got that corner there. That's probably a cusp, actually. And then I've got this jump in the graph right here that means it's not differentiable there either. So those are the two places where this function is not differentiable. So I say everywhere but, I can take the derivative everywhere else, find the slope of the tangent line, no problem, anywhere but those two places. Okay? Now the next section of the test really just has us finding the derivatives. So again, I'm going to write them all down, and I'm going to, in fact, what I'll probably do is I will write the answers, I'll pause it, I'll write the answers, then I'll start the recording again so that you can see the answers, and if there's anything that I feel like you need to see or that's important, I'll take the time to say where I got that answer. So give me just a second, and you'll see the answers here momentarily. All right, guys, so here are the answers for each of these problems. Now, a couple things that I just do want to mention is when you use the power rule, like on a problem like this one where I take the 2 down, I still multiply, even though there's a fraction there, I still multiply it by 1/8, and that's where the 1/4 comes from. Also, don't forget that x to the first power, when I take the derivative of that, the constant number stays out front, but the x goes away. Here, I want to make sure that we understand that this is a product rule between 2 sine of x and cosine of x. So I go to take the derivative, and that's what I get down there. Number 8, that's a quotient rule. Remember, that's the bottom function multiplied by the derivative of the top function minus the top function times the derivative of the bottom, all over the bottom squared. And we never simplify. Don't worry about simplifying when you find derivatives. Couple of things here. I changed this to x to the 1/2 power. Then I used the power rule to take the derivative of that. And then I could have used the quotient rule here, and there's nothing wrong with that, but I wanted to make that be a little bit easier, so I made that be x to the negative 1/2 power instead of the positive 1/2 power on the bottom, so it made it easier to take the derivative because then I didn't have to use the quotient rule. On 10 and 11, both of those, I used the product rule. Hopefully those ones are fairly straightforward. Again, check your work versus what I have here, and if you have any questions about how I got the answers I did, I might have screwed them up. I did them kind of quickly. Just let me know. Kind of the same thing here. Okay, there's nothing real weird going on. I do want to say right here when we have x to the negative 1, we do bring the negative 1 down. Don't forget we subtract 1 from the power. So negative 1 minus 1 is negative 2. That's where that negative 2 comes from. It's not 0 because negative 1 minus 1 is not 0. These are kind of long, but they're not bad. They're just the quotient rule. One thing that you can do on the quotient rule to help you out a little bit is you'll notice on number 16 here, I multiplied the top out before I took the derivative. That makes it a little bit easier because if I had looked at this problem and I'd said, okay, when I go to take the derivative of the top, I would have had to use the product rule. Now, there's nothing wrong with that, but the less rules that you have to apply while you're taking the derivative, usually the better it is for you. So in this case, that's why I did what I did. I didn't have to, but it made it easier for me to look at. Don't forget as well that when we take the derivative of any constant number, it doesn't matter what that number is, the derivative of that is always 0. A lot of these are fairly straightforward. You'll notice on this one, because this is the square root of 4x, I can take the square root of 4 and the square root of x separately, so I can rewrite this as 2 times the square root of x, which makes it a lot easier to deal with. And really down here, I could have combined or canceled, if you will, because 2 times 1/2 is just 1. So I really could have just written x to the negative 1/2 power right there. Now, I will say as we look at these that these are more difficult than what you would see on the test. So just be aware of that. Here, one thing that I do want to focus on is that the product rule still works fine when we're multiplying 2 trig functions together. So I just first times the derivative of the second plus second times the derivative of the first. There's more words going on, but the answers are still, we still write them the same way. They're longer, okay? Same thing on number 23. Now, one thing I do want to focus on number 23 is I have a function, and then there's a minus sign right there. That means I am starting another term. We always take derivatives one term at a time. So here, this x that we're looking at is not part of that x. It's not x minus x. It's x minus all of that stuff. So I take the derivative of x, that becomes 1, and then the rest of this stuff is just the product rule from x times the cosine of x. On these ones, again, just because we're using trig functions doesn't mean that anything is different from those. You just get longer answers. So on 24, I used the product rule to come up with what I got. Notice I did take the derivative of 1 minus the cosine of x. The derivative of cosine is negative sign, so 2 negatives make a positive. That's where that positive came from there. Everything else I feel like is pretty straightforward there. I used the quotient rule here. And then here, derivative of cosecant and secant, both are much longer, but I just did it one term at a time. Nothing's multiplying there. So I was able to find that derivative. These ones are both very long, but I use the same thing. I've got a product or quotient rule on 27, a product rule on 28. Both of those, again, hopefully you can see where I got the answers that I did for both of those. And if any time, I'm sure you did this already, but if any time you needed a little bit more time to look at the answers so you could really see what I did, Obviously, you just hit pause anytime during the video, and you can do that. I just want to make sure that you have all those answers down. Now, number 29 says that I need to find the third derivative. What that means is I just take the derivative of my original function. So in this case, I get 30x to the fifth minus 12x squared plus 3. That is what is known as the first derivative. If I take the derivative of that, again, just using the power rule here, that is what is known as the second derivative. And if I want to take the derivative of that, that is what the third derivative is. So this would be my answer. The focus here is knowing if you're asked to take any sort of like ranked derivative, if you will, that's just telling you how many times you need to repeatedly take the derivative of that particular function. On number 30, he wants us to find the 447th derivative of cosine. So what we do is we take 447 and we divide it by 4, excuse me, because that's how long it takes to cycle through all of the different sine, cosine, negative cosine. Anyway, we talked about that in class a little bit. When you do that, you get 111.7, I don't know why I wrote a 4 there, 75. The 0.75, if I look at that as a fraction, that is 3/4, which means I am 3/4 of the way through the cycle before it starts over. So my first derivative here is negative sine of x. My second derivative is, and then our second derivative here, would be, hopefully you can see this, would be negative cosine of x. And then my third derivative, which is what we're looking for in this one, would be positive sine of x. Now again, you really could do all 447 derivatives if you really wanted to, but this 111.75 is telling me I cycled through completely 111 times, because if I took the fourth derivative, I would be right back at the cosine of x. So I've cycled through 111 times completely, got back to the cosine of x, then I'm 3/4 of the way through, which means my derivative is the sine of x. And that one actually will not be on the test, just so I don't believe I put that on the test. I hope not. If I did, just divide it by 4, find out kind of what the remainder is, and that'll tell you what the 447th derivative of cosine of x is. Now lastly, when we're drawing the derivative, don't forget that anywhere the graph has a max or a min, we have our derivative graph crossing the x-axis. Before that time, my graph is increasing on number 31, and then it's decreasing, and then it's increasing again. And that's not a real good picture. In fact, it's a really bad picture. But that is roughly what the derivative would look like on that one. Now, on number 32, actually, I want to look at number 33 real fast, then we'll come back to 32. Notice this one is decreasing the entire time. It's really steep at first, and then it levels off, and it becomes really, really shallow. Because it's decreasing the entire time, the derivative is going to be below the x-axis the entire time, and that is what my derivative would look like. Now on number 32, and we haven't talked about graphs like this very much, but on number 32 you'll notice that I have a weird looking piecewise function. And if I wanted to draw the derivative of this graph, I'd have to just basically draw it one piece at a time. Now one thing to note here is just because the derivative is connected does not mean, or excuse me, the original is connected does not mean that the derivative will be as well. In fact, this one, the way I draw this one is it would kind of come down like that. Then all of a sudden notice that this is a positive, that this is a line that's just a straight line that has a positive slope. And it has a positive slope of 2 if you care. It doesn't really matter. So I would draw a straight line right there. Then all of a sudden it flattens out up here. So, whoops, that's not the derivative. I was showing that that flattens out. The derivative would be down here. So that is the derivative of that one. And then it has a slope of -2. And that would be this. That is what the derivative would look like. There's nothing wrong with having a jump in your derivative graph as long as you're like relaying what is really happening in that particular problem. So I know this video is quick. That's all of the answers that you would need for this. If you have any questions about this, please let me know so we can get you ready for the test.